Hello everyone. We know statistics can be used for comparing various things. So today we'll be discussing testing of hypothesis when we have more than two things to compare. So here is a brief outline of today's lecture. Firstly, we'll get to know more about what is design of experiments, and then we'll study some methods when we have multiple means and we need to compare those multiple means. So what is design of experiments? Now these are three basic principles of design of experiments. First one is replication. Now what is replication? When we perform any experiment, it's better to have repetitions because the measurements that we do are prone to some errors. They are prone to some local conditions which we cannot control. So it's better to have repeated measurements so that we can be more sure about our outcomes. So these repetitions is known as replication. Then second principle is randomization. So randomization is basically done by assigning treatments randomly to the different units. For example, I want to study the effect of two different teaching methods on the comprehension level of students. What I can do is, I can select two divisions. To one division, I would teach using one method. To other division, we would use other method of teaching, and then finally record the scores of the students on some comprehensive test and then compare the readings. But then, it might happen that the division of students might be already decided on the basis of their intelligence level and so on. So there might be some effect due to the original intelligence of student. So that's why I need to assign treatments randomly rather than some systematic pattern, so that such variation due to the original variation in the units would be eliminated in my final effect. So this is the principle of randomization. And then there is one more thing which is known as blocking. For example, we are studying some production process and how much time does it take to get whatever output we want. So there might be different methods. So on the first day, we produce things by using one method. On the second day, suppose we produce things by using another method. And we may compare the result. Now again, if I change in one day, I cannot perform my entire experiment. There is a time constraint. So, half of the things I do today, half of the things I perform tomorrow. But then, my environmental conditions for today and tomorrow are not exactly same. There are temperature changes, humidity of the air changes. So, these are the things which may affect my final result. So, I need to take care of such variations. So, in such cases, I may consider my days as blocks and first remove effect due to differences in these days and then study what is the actual effect of my change in the treatment. Hence, replication, randomization and blocking, these are the three basic principles which we have to keep in mind before designing an experiment. And once we design an experiment, after doing all these things, then we have to use it for our purpose. And what is our purpose? We have to basically use it for comparing means of more than two groups. Now, though we have to compare the means, we do it through the study of the variations in these treatments. So, this kind of statistical tool is known as analysis of variance. The basic principle of analysis of variance involves splitting of variation. So what we know is, if we have different treatments, then they are going to produce variations. What we do is split the variation into two components. First is variation from known sources, which can be, say, our treatments or blocks. And then second component is the random error component or random noise, which we cannot eliminate. This is like a background noise which cannot be eliminated, so we have to take care of that also. So what we do is, we measure the variation from known sources, variation from unknown sources, and see if the variation from known sources is actually significantly high or not. If it is high, then it would mean that our treatments or blocks that we are studying are significantly different from each other. Here is a basic model for one-way ANOVA. One-way ANOVA assumes that there is only one known source of variation. For example, if I want to test, say, effect of different fertilizers on crops. So I am applying different fertilizers. So my fertilizers is the only source of variation, and other things are assumed to be common for all the fields. So this is the basic mathematical model. My Yij represents jth observation on ith treatment. So here it would mean jth crop field which has received ith fertilizer. Then mu is the overall mean effect. It is a common effect. Tau I is the effect due to ith treatment. So it is the specific effect of the ith fertilizer, and epsilon ij denotes the random error component. And here you can see the range of I is 1 to k, means basically I have k different treatments, or in the example k fertilizers, and my j goes from 1 to ni, means ith fertilizer is applied to ni fields. So my j goes from 1 to ni. So you can notice that I don't need to replicate each treatment equal number of times. I can have variable number of replications, and still I have a mathematical method for doing the analysis. Now our problem of interest is to see whether these treatments or whether these fertilizers are actually different. Is one of them actually more effective than others or not? So my null hypothesis is that of no difference. So my H0 is Tau1 equal to Tau2 equal to Tau k, means all these treatments have same effect. They are identical. And my alternative hypothesis H1, as we know, is negation of H0. So it says that at least one treatment is significantly different from other treatments. So we have to remember that my H1 doesn't say that each and every treatment is different. What it says is at least one treatment is significantly different from others. It may happen that only one fertilizer is better, others are almost equal. In that case also my H0 is going to get rejected. Now if I come to know if my H0 is rejected, then what I conclude is at least one effect or at least one treatment is different. But then obviously I won't be happy with only this knowledge. I need to know which one is different. So for that we need to go to pairwise comparison methods. So if my H0 is rejected, means if I conclude that at least one of them is different, then I would compare them pairwise by using any of the methods listed here, and then through pairwise comparison we can see which is the thing that is different. There might be, say, out of 10 there might be, say, 2-3 which are different than others. So we can categorize these treatments into groups of similar and different. So these are the various methods: Stucky's test, Fisher's least significant difference, Chaffee's test, Duncan's test, and Dunnett's test. Dunnett's test is basically used when I want to do something like comparison with a control. For example, we are in drug business, and if I want to introduce a new drug and prove that it is better than the existing drug, then existing drug may be used as a control. Here is one illustration. In an experiment testing the effectiveness of different food supplements on the milk yield, a sample of 30 cows was divided into 4 groups. The cows in group 1 received no food supplement, so it was treated as control group, and those from group 2 to group 4 received different food supplements, say A, B and C. And now this is how the data looks like. For each group I have 4 observations, and then using these 4 observations we can carry out analysis of variance using standard softwares. We would get p-value. If the p-value is less than the level of significance, which might be, say, 0.05 or 0.01, then we would conclude that these food supplements are different, at least one of them is different, then we can go for pairwise tests and see which food supplement is best and so on. So these are our steps. Firstly, we would test the hypothesis that the food supplements affect the milk yield. If all of them are having almost same effect, then it would mean that there is no difference and the hypothesis of interest, null hypothesis, would be accepted. But if the null hypothesis is rejected, then we may go to pairwise comparisons, for example say Fisher's LSD or Tukey's, and then compare the pairs of food supplements and then do conclude which one is the best. But then sometimes one-way ANOVA may not be sufficient. There might be more than one sources of variation which we cannot control. So in such cases, we need to go to what is known as two-way ANOVA. So in two-way ANOVA, we have two known sources of variation. So model will be slightly modified. In the one-way ANOVA model, we had only two subscripts for Yij. One subscript was for treatment number, another subscript was for observation number in that treatment. Here we would have two sources. One source of variation is treatment and another source of variation is block. So we have three subscripts. We have Yijk, which represents kth observation in jth block receiving ith treatment. My mu, as in case of one-way ANOVA, is the overall mean effect which is common to all the observations. Tau I is the effect due to ith treatment. Beta j is the effect due to jth block, and Nij is the number of observations in jth block receiving ith treatment. So here I have A treatments, B blocks, and in ith treatment and jth block I have Nij observations. So here also I need not have equal number of observations in block or equal number of observations in treatment. Even with variable numbers we can proceed with the analysis. Now here I can test two different types of hypothesis. First is that all the treatments have same effect. That is, my H01 would be tau 1 equal to tau 2 equal to tau k. So no treatment is significantly different than the other treatments. And another hypothesis of interest can be all the blocks have same effect. So say beta 1 equal to beta 2 equal to beta k. And corresponding alternative hypothesis would be at least one treatment is significantly different from others and at least one block is significantly different from others. Now here is an illustration for the same. So this table gives us observed response time in seconds for 12 animals in a study of the effects of 3 different diets and 4 different drugs on time of response to a certain stimulus. So what we have is, we basically have 12 observations in interest drugs, but then the thing is, the animals on which we are testing these drugs, they receive different kinds of diets. So there might be some effect of diet also. So we need to take care of that diet effect, and that's why we cannot ignore this diet as a source of variation. We need to incorporate that also. Hence, we can treat diets as blocks, types of drugs as treatments, and then carry out two-way ANOVA using standard software and see what is our conclusion. Now next important thing is analysis of covariance. What we did in one-way ANOVA and two-way ANOVA was that in one-way ANOVA we had one source of variation, in two-way ANOVA we had two sources of variation. We can have more than two sources of variation also. We can go for three-way things. But then the problem with both the methods was our sources of variation were categorical. We had only 4 type of treatments or something like that. But if I have a continuous variable which brings some variation in the data, then I need to take care of that variable also. So I cannot use one-way ANOVA or two-way ANOVA if my source of variation takes some continuous values. So in such situations, we go for what is known as analysis of covariance. So it is basically used when my source of variation is a covariate, it's not a factor. Now what is a factor? Factor is a categorical variable which affects my response, and covariate is a continuous variable which affects response. So if I have some covariates also in my data, then I can use analysis of covariance. We'll see one example where this can be used. So here we have similar kind of experiment as in two-way ANOVA. We are studying the response time for some stimulus in some animals, but then we know that older animals may give later responses. So the age of that animal may come into picture and it may bring some variation. And now we know age is a continuous variable. So we can use age as a covariate here. So what we have is, we have data on 15 animals and we have 3 drugs again, drug 1, drug 2, drug 3, and we want to study which drug is better, which reduces the time of response to a stimulus. Time of response to stimulus is recorded in seconds, it is denoted by variable y, and age of those animals in months is recorded as x. So this response y depends on two things. It depends on the age of the animal as well as the drug on which that animal is being treated. So for studying the effect of drugs, we are going to first eliminate the effect due to age, and then we would be studying which drug is better and so on. So analysis of covariance can also be performed using standard softwares through commands which are available for general linear model type of structures. So here also we'll get p-values, and using those p-values we can interpret whether my drugs are effective or not. But then still there are few more things which need to be studied. For example, we said that we can have one-way ANOVA for one source of variation, two-way ANOVA for two sources of variation, and so on. But if suppose we have a large number of sources of variation and then each having many levels, then in such cases, for getting accurate results using regular ANOVA things, we would need hundreds of observations, because larger the data, then only we can be more sure about our conclusions. But then it may not be practically feasible to have so many observations. So in such cases, we can use what is known as factorial designs. So factorial designs have some specific mathematical structure due to which even number of functions we can study effects of many factors and then conclude about the optimal level of factors which would give us maximum yield. And then similarly there are some things where we may be needing some interpolation or some extrapolation, so where we might want to see what combination of different treatments can give us the best results. So in such cases there are variety of tools known as response surface methodology. So they also have some mathematical formulae and some graphical displays due to which we can conclude which is the best setup for running the experiment that we have with us, and which can give us maximum production with say less input and so on. So these are some of the other design of experiment tools which are also available in standard packages, so you can explore them if you wish. I would stop here. Thank you.